Cement is a crucial building material that serves as the foundation for many construction projects, from towering skyscrapers to humble sidewalks. Its production involves a complex process that combines various raw materials and precise chemical reactions to create the sturdy and durable substance we rely on in the construction industry. This is how cement is made. The first thing we need to have clear is what cement really is. Cement is a binding material that, when mixed with water, forms a paste that hardens over time. This hardened paste, known as concrete, when mixed with aggregates like sand and gravel, is widely used in construction for its exceptional strength, durability, and versatility. The history of cement dates back thousands of years to ancient civilizations like the Egyptians and Romans, who used various natural materials to create rudimentary forms of cement. However, the modern cement we know today is the result of centuries of development and refinement. The cement that we see today, however, is credited to Joseph Aspdin of Yorkshire, England. In 1824, he took out a patent for a material that was produced from a synthetic mixture of limestone and clay. He called this product Portland cement since it looked like something called Portland stone, an important component of buildings made at the time. Even in 1824, this version of cement was rudimentary, and it took 200 years between then and now of constant work and cutthroat competition to truly make cement the well-known building substance it is today. So, how does cement really get made? The production of cement begins with the collection of raw materials, which are essential for the chemical reactions that will ultimately yield cement clinker, the intermediate product that can be further processed into various types of cement. The primary raw materials required for cement production are limestone, clay or shale, and iron ore. Additionally, various secondary materials may be used to enhance specific properties of the final product, or to reduce environmental impacts. These secondary materials include fly ash, slag, and natural pozzolans. But before we can get into the actual process, we should first talk a little about the various constituents of cement. Limestone is the primary source of calcium in cement production. It is a sedimentary rock primarily composed of calcium carbonate and is formally written as CaCO3. The limestone used in cement production is typically high in purity, with minimal impurities like silica, alumina, and iron. Then there are clay and shale, which are rich in aluminium and silicon. Both of those are crucial ingredients in cement, as they provide the necessary alumina, Al2O3, and silica, SiO2, content required for cement clinker formation. The choice between clay and shale depends on local availability and the desired properties of the final product. That brings us to iron, or more accurately, iron ore. Iron ore in the form of iron oxide such as hematite, Fe2O3, or magnetite, Fe3O4, is used to supply iron Fe to the cement-making process. Iron is essential for the formation of calcium silicates and illuminates, key components of cement clinker. Secondary materials, often referred to as cementitious additives, can be used to improve certain characteristics of cement and reduce its environmental impact. These materials include fly ash, slag, and natural pozzolans. Fly ash is a byproduct of coal combustion, slag is a byproduct of iron and steel production, and natural pozzolans are naturally occurring materials with cementitious properties. Alright, now that we know what cement is made of, it's a simple question of how we can get those materials. The first step in cement production is the extraction of the raw materials, which typically involves mining or quarrying operations. The goal is to obtain high-quality limestone, clay or shale, and iron ore that meet the specific chemical composition requirements for cement production. Limestone is usually obtained through open-pit mining or quarrying. Large drilling rigs and explosives are used to break the limestone into manageable-sized blocks. These blocks are then transported to the crushing plant, where they are crushed into smaller pieces. Clay and shale can be found near the surface or underground. In some cases, they may require blasting or drilling for extraction. Once extracted, they are transported to the processing facility for further preparation. Iron ore can be mined from open pit or underground mines depending on its location and accessibility. The extracted iron ore is then transported to the crushing and blending facility. After the raw materials are extracted, they go through a series of preparation steps to ensure their suitability for cement production. The limestone blocks are crushed into smaller pieces by crushers. The resulting crushed limestone is then transported to a storage area. Clay and shale may contain impurities, so they are carefully screened and processed to remove any undesirable materials. The cleaned clay and shale are stored separately. Iron ore is crushed into smaller pieces and blended with other raw materials, ensuring a consistent iron content throughout the process. To achieve the desired chemical composition, the crushed limestone, clay or shale, and iron ore are mixed together in the appropriate proportions. This mixture is known as the raw meal and helps ensure the quality of the final product. The next crucial step in cement production involves the precise combination of the prepared raw materials to create a homogeneous raw meal with the correct chemical composition. The raw meal serves as the feedstock for the kiln, where the chemical reactions leading to clinker formation take place. The raw meal is fed into a raw mill, which is a rotating cylinder equipped with grinding media, balls or rollers. Inside the mill, the raw materials are ground into a fine powder. The choice of grinding equipment and process parameters is critical in achieving the desired particle size and consistency. To ensure uniformity in the raw meal, it undergoes a homogenization process. This process typically involves blending the ground raw materials in storage silos and using automated systems to extract and mix the materials in a controlled manner. Homogenization helps eliminate variations in chemical composition. The heart of the cement manufacturing process is the rotary kiln, where the raw meal is subjected to high temperatures and chemical reactions that transform it into clinker. The kiln is a large, cylindrical, rotating furnace with a carefully controlled temperature profile. Before entering the kiln, the raw meal passes through a preheater, which uses the hot gases from the kiln to heat the raw meal. This preheating stage reduces the energy consumption in the kiln by preheating the raw materials and partially calcining them. As the raw meal moves through the kiln, it experiences a series of temperature zones. In the lower part of the kiln, at temperatures around 700 degrees C to 900 degrees C, carbonates in the limestone decompose, releasing carbon dioxide, CO2, and leaving behind calcium oxide, CaO. This process is known as calcination. As the temperature increases further, the remaining raw materials undergo complex chemical reactions. Silica SiO2 from the clay or shale reacts with calcium oxide CaO from the limestone to form calcium silicates, Ta3, SiO5, and Ca2, SiO4, and other compounds. These calcium silicates are the primary constituents of clinker, the intermediate product of cement production. The clinker produced in the kiln is extremely hot, with temperatures reaching up to 1,400 degrees Celsius to 1,500 degrees Celsius. To prevent the clinker from prematurely hardening, it is rapidly cooled using air or water. This cooling process is crucial for the quality of the final product. The clinker obtained from the kiln is coarse and needs further processing to become the fine powder that we recognize as cement. Clinker grinding is the final step in the cement manufacturing process and involves finely grinding the clinker along with a small amount of gypsum to control setting. The cooled clinker is temporarily stored in clinker silos before being sent to the grinding mills. The clinker is finely ground in a series of ball mills or roller presses. These grinding mills use various grinding media such as steel balls or rollers to reduce the clinker to a powder with the desired fineness. During the grinding process, a small amount of gypsum, calcium sulfate dihydrate, is added to control the setting time of the cement. Gypsum slows down the hydration of the cement particles, preventing them from setting too quickly during mixing with water. Once the clinker is ground to the desired fineness and mixed with gypsum, it is ready to be packaged and distributed to construction sites and retailers. The final product is known as ordinary Portland cement OPC, but additional additives can be included during the grinding process to produce specialized types of cement with specific properties. The finely ground cement is stored in silos before being loaded into bags or bulk containers for distribution. Bagged cement is commonly available in various sizes, such as 50-kilogram bags. Quality control measures are implemented throughout the manufacturing process to ensure the cement meets the required specifications and standards. Samples are regularly taken and tested for chemical composition, fineness, and other properties. Cement is transported to construction sites, wholesalers and retailers by trucks, trains, or ships, depending on the location and scale of distribution. Cement production is a resource-intensive process with significant environmental impacts, primarily due to the release of carbon dioxide, CO2, during the calcination of limestone. As concerns about climate change and sustainability grow, the cement industry is actively working to reduce its environmental footprint. Here are some key strategies and considerations. For one, some cement producers are exploring the use of alternative raw materials such as industrial byproducts and waste materials to replace traditional raw materials partially. This can reduce the environmental impact and conserve natural resources. Cement kilns can be powered by alternative fuels like biomass, waste-derived fuels, or even non-recyclable plastics. Using alternative fuels can reduce the carbon footprint of cement production. Research is ongoing in the development of technologies that capture CO2 emissions from cement plants and convert them into useful products such as synthetic fuels or building materials. Improving the energy efficiency of cement plants reduces both energy consumption and CO2 emissions. Modern kilns are designed to use waste heat for power generation and incorporate energy-efficient technologies. Some specialized cement types, such as low-carbon or blended cements, have a reduced carbon footprint compared to traditional OPC. These cements are designed for specific applications and environmental goals. Cement production is subject to environmental regulations that aim to limit emissions and promote sustainable practices. Compliance with these regulations is a priority for the industry. Cement production is a complex and resource-intensive process that begins with the extraction of raw materials and ends with the grinding and packaging of the final product. Each step in the process plays a crucial role in determining the quality and properties of the cement. As the construction industry continues to grow, the demand for cement remains high. However, there is also a growing awareness of the environmental impact of cement production, particularly in terms of carbon emissions. The industry is actively working to reduce its carbon footprint through various strategies, including the use of alternative raw materials, fuels, and energy-efficient technologies. The production of cement is a testament to human ingenuity and engineering, as it involves precise chemical reactions and careful control of temperature and materials. It is a vital component of the modern world, enabling the construction of infrastructure and buildings that shape our lives. As we move toward a more sustainable future, the cement industry will play a crucial role in finding innovative solutions to reduce its environmental impact while continuing to meet the world's construction needs.